Okay, so let's move on. And our next speaker is Tamás Gombor, who will talk about wrapping corrections for long-range spin chains. So please.
Thank you. At first, I would like to thank the opportunity to present my recent result on long-range spin chains. And the goal of this talk to show you how to define spin chain interaction when the range of the interaction is larger than the length of the spin chain. This is the contents of my talk. I start with the motivation part. After that, I show the definition of the asymptotic long-range spin chain. And after that, I show a construction for transfer matrices for this long-range chain. We will see that this transfer matrix gives a method to define finite size long-range Hamiltonians, and I finish my talk with some requirements coming from the ADS-CFT duality. Okay. Actually, I have an easy job in the motivation part because my motivation comes from the topics of the previous two lectures. So we saw that in n equals for super Young mills, some quantities like defect bound point function and the 3-point function of determinant operator, and also 1-point function in this RP4 n equals for super Young mills. So these quantities are connected with an overlap between boundary state and Bethe states corresponds to the single trace operators. And there are lots of results for these overlaps, for example at tree level, and also some results at strong coupling, and also for finite coupling, but this finite coupling results mostly concentrated on the asymptotic region. And the most important open question, how we can calculate the wrapping corrections for these quantities. For more details, let me give a brief review for the integrability approach for calculating the 2-point function of the ADS-CFT, which is of course well-known stuff. So we have two sides gauge. At the gauge theory side, we have long-range spin chain with length j, and the string theory side, the theory can be described by the one-dimensional sigma model with length j. And at the asymptotic limit, when the length goes to infinity, from the perturbation theory, the dilatation operator can be calculated, and the leading order is 2-side interaction, next order is 3-side interaction, and so on. And this dilatation operator is integrable, which means there exist higher charges, for example, this Q3, for which the leading order is 3-side integrable, the second order is 4-side integrable, and so on. Because of the integrability, the spectrum can be obtained from an asymptotic beta ansatz. And we have to note that this Hamiltonian for the n equals for super Young mills is a very complicated object because the local space, so the local Hilbert space is infinite dimensional, and also there is a dynamical effect, which means that the Hamiltonian can change the length of the operator. For example, 2 fermion can scatter to 3 scalar. And for these reasons, it's efficient to use some toy models for develop methods and test the ideas. And so good toy models can be the long-range deformation of the GLN spin chain, for example. Okay, at the string theory side, the anomalous dimension are the string energies, and infinite lengths, the dispersion relation and the scattering matrices are known, and this defines the spectrum, and this infinite length, the spectrum is given by the asymptotic beta ansatz, And the toy models for this setup is the simpler 1+1 dimensional field theories. And of course, the asymptotic Bethe ansatz in the two descriptions are the same. And what happens at finite lengths? So for lengths which are, for the perturbation order, for which the range of the interaction is bigger than the length of the chain, the asymptotic Bethe ansatz cannot work anymore, and wrapping corrections appears. But there is no good spin chain description for these wrapping effects. So in other words, we haven't got any method which tells us how to define interactions in a spin chain where the length of the chain is smaller than the interaction range. And the solution for the wrapping correction comes from the field theory description. In the field theory, we know so the finite size correction appears at finite lengths, and this finite size correction agrees with the wrapping correction coming from the dilatation operator. And all the finite size correction can be handled with the thermodynamic Bethe ansatz, and of course there are more sophisticated techniques based on the Y, T, and Q systems. And these methods was so successful that the investigation of the long-range spin chain stopped at the asymptotic level. But for other quantities, for example, the G function, some problem appears when there are bound states in the spectrum, and the excited TBA equation cannot be simply obtained by analytic continuation. So therefore, other methods are necessary to calculate such quantities. That is why I think it's worth to come back to the spin chain description and find how to define spin chain where this wrapping effect can be investigated. And I think this can be open new perspectives for calculation in the ADS-CFT, the planar limit. Okay, let's continue with the basics of the asymptotic long-range spin chain. As I mentioned, dilatation operator can be written as a series expansion, and Hamiltonian, the interaction range of the Hamiltonian grows by order of the coupling constant, and I use this notation HL for the order L in lambda, and this HL is a Hamiltonian with interaction range L plus 2. And clearly this Hamiltonian is defined only for the lengths which are bigger than the interaction range. So this is the asymptotic region for this order of the perturbation theory. I also use some graphical notation for this Hamiltonian. So for example, this is the nearest neighbor Hamiltonian, and this is the Hamiltonian with three-side interaction. For integrable Hamiltonian, there exist higher charges, for example, Q3, and this Q3 has these interaction ranges. And we can expand this equation order by order. The leading order is the usual integrability condition for the nearest neighbor model. At the first order, we have a non-trivial condition for H1 and Q13. And the second order, we have a new constraint for H2 and Q32. Using this equation, starting from an integrable two-side spin chain, we can obtain these higher Hamiltonians order by order. And for the explicit calculation, we know that there are unfixed parameters. The first class of the sum-fixed parameter comes from the similarity transformation of the charges, which is obviously defines commuting charges. And this U is just the sum of local operators, and these coefficients epsilon are spectral parameter dependent on fixed parameters. And the second class comes from the fact that the linear combination of the charges also define the commuting set. And we can see that this gamma has no effect on the eigenvalues, and this epsilon has no effect on the spectrum. Therefore, these are unphysical parameters. The physical parameter can be obtained, the argument of this paper. So if the derivative of the charge with respect to the coupling constant is a commutator, and for leading order these sets of charges are commuting, then it is a consequence that these charges commuting at finite coupling as well. The only consistency condition is that this commutator has to be a local quantity, and there is two choice for this X operator. It can be a boosted version of conserved charge and also a bilocal combination of conserved charges. So in this X, two new type of parameter appears. And in the next slide, we will see these are physical parameters. So let's see an example for a long-range deformation. So for the original XXX spin chain, it is well known that the spectrum can be obtained from the Bethe Ansatz equation, where this U is the rapidity parameter, and this equation connects the momentum and the rapidity parameter, and the charges are just sums of local densities. And it turns out that long-range deformation, the Bethe Ansatz is modified in two ways. So we have to redefine the connection between the rapidity and the momenta, and a new scattering phase appears in the equations. And it turns out that this alpha parameter defines this rapidity map, and the beta parameter defines this extra phase. And the gammas are just the linear combination of the charges, and we see that the epsilon parameter is completely disappear for the spectrum. Okay, so let's continue with the construction for the transfer matrices. This construction based on the recently introduced algebraic framework for medium range spin chains in these two papers. So we call a spin chain medium range if the interaction range is bigger than 2 but finite. So in this, so I will use this notation for the L+2 site interactions. So we can see that this Hamiltonian is a sum of densities, and this density operator acts on non-trivially on L+2 site, and also use this shorthand notation for the density with interaction range L+2. And it is clear that this Hamiltonian is also is only defined for lengths which is bigger than the interaction range L+2. And I also use a notation for this density operator. So this is a 6-site interaction example. And we define Lax operators with this regularity condition, which is, so we restrict the leading orders in the spectral parameter. So the leading order is just the identity operator, and the second order is a Hamiltonian density operator. So this Lax operator has the same interaction range than the Hamiltonian density. And this is the graphical interpretation for this regularity condition. So the spectral parameter dependent Lax operator is equal to the identity plus U times the Hamiltonian and other terms. We also introduce an R matrix which has interaction range 2L+2, and this satisfy the RLL relation. And this is the graphical interpretation for the case when the interaction range is 5. So this red box is the R matrix, and these are the Lux operators. And if we commute the R operator, so the action of this commutation is that the rapidity parameter are changes in the Lux operator. So this is the RLL relation. And we can also define transfer matrices, which is a product of shifted Lux operator. And also we introduce this shifted or twisted trace. So for interaction range 4, we introduced 3 auxiliary space. And we have to trace out this 3 auxiliary space in this twisted way. So we take the first incoming leg and sum with the j plus 1 outcoming leg. And we trace out the second incoming leg with the j plus 2 outgoing leg, and so on. So this is the definition for this twisted or twisted trace. Okay, so this is the definition of the transfer matrix. So be more familiar with this notation. Let us show some properties of the transfer matrix. So at first, let us start with the definition of the transfer matrix. We can add an extra site. So in this side, the Lux operators acts trivially, and after doing the summation with this outgoing at this incoming node, we obtain just the previous diagram. But in this case, we can see that there is summation for these 4 incoming legs. Therefore, we can replace this Lux operator to that place, which is just the cyclicity property of the twisted trace. And now, this Lux operator acts trivially on this first side. So therefore, we can do the summation for this incoming and this outgoing leg. And doing this summation, we obtain this diagram. So we can see that this is the original transfer matrix, but we did a shift, a cyclic shift in the outgoing and the incoming legs as well. So with formulas, this relation tells us the transfer matrix is invariant with respect to this cyclic shift, where this U is the shift operator. Okay, let's derive another property of the transfer matrix. So if we take this diagram, where this red box is just an R matrix, and I review the RLL relation for this situation. So we can see that we can apply the RLL relation for these 3 operators. So we have to shift this red box with one side to the left, and also we have to change the spectral parameters in the Lux operator. And we can see that we can obtain again, well, we can use again the RLL relation. And repeating this method, we obtain this diagram. So now we can multiply the 2 sides of the equation with the inverse of this R matrix and take the twisted trace with this 6 auxiliary space. So now we can see that we can replace this R matrix to there using the cyclicity property of the twisted trace. So we obtain this diagram. And so these products of Lux operator is just the transfer matrix, and these products are the shifted transfer matrix. And this is true for the other side. And using the fact that the transfer matrix is invariant under the shifts, we obtained that the transfer matrix defines commuting quantities. So this is just the integrability property. Okay, so let's continue with the generalization to the long-range case. For this, I define the truncated locks and R operators. So these calligraphic letters means that these depend on the spectra, the coupling lambda. And we define this level L locks operator as a series expansion in the coupling constant up to order lambda to L. And we define also this level L R matrix as a series expansion in the coupling. But in the definition of this level L locks operator, we use the previous L operators. So for level L operator, it contains the locks operators of the previous levels for lower L's. But for the R matrix at level L, we use completely different R matrix for each level. So in the series expansion, these R operators have two indexes. The first index labels the level, and the second index corresponds to the order in the coupling. So this definition needs for the consistent algebraic definition. We will see the details now. So we define the RL relation just as for the medium range case, but now we define this in a truncated way. So we have so this equation is satisfied only for this order. So this is a L+1 equation for these orders in lambda. And now let us assume that there exists a solution of this equation. So there exists a level L locks and R matrices, and let us take a next order. So next level equation for L+1, which looks like this. So for the first L+1 order, this equation contains only just L matrices 0 to L. Or in other words, if we neglect the highest order of this equation, we just remain only this first L+1 order. This equation looks like this. So in this order, the L+1 level Lux operator becomes the L order Lux operator because of this definition. And we can see that this is a completely different requirement for this level L Lux operator as the defining one. So if we go higher and higher levels, new and new requirement appears for this level L Lux operator, which is obviously not a consistent definition. But this can be consistent if it is guaranteed that these new equations appearing at the higher levels are exact consequences of the first definition for this Lux operator. And this turns out this is the case. So neglecting the highest order of this matrix, the first L+1 order can be obtained by the level L quantities, where we introduce the formal inverse of the Lux operator. So using this definition for the next level R matrices, this equation is a consequence of this. And we can see that this Lux operator, where the first index is bigger than the second, are fixed completely by the R operators with the coinciding in the upper indexes, which means that in this construction, the real unknowns are this LL matrices and this RLL. And the only non-trivial condition appears from this truncated error relation at the highest order, so for order lambda 2L. And this is this equation in that order, and we can systematically solve this equation, obtaining higher and higher order L and R matrices. And this is the only requirements for this expressions. Okay, so now we can define the transfer matrix, and we define it with this truncated way. So use the same definition as was for the medium range case, but truncated at order lambda 2L. And one of the consequences of the truncated error relation that this transfer matrices define commuting quantities up to order lambda L plus 1. And we also require this regularity condition for the Lux operator, which is the same as before. So the leading order in the spectral parameter is just the identity, and the second order is just the Hamiltonian density. And the Hamiltonian density can be series expand, and the interaction range of this operator agrees with the operator ranges in the definition of the asymptotic long-range Hamiltonians. So this interaction range is k plus 2 at order k. The consequences of the regularity conditions are the following. So the first one is the transfer matrix is the identity at u equals 0. And the first derivative at u equals 0 is just the Hamiltonian, which can be series expand. And for lengths which are bigger than the interaction range, these Hamiltonians are just sum of densities, and then this HL has interaction range L plus 2. And this is agrees with the definition of the asymptotic long-range Hamiltonians. So the regular solution of this truncated error relation gives integrable long-range spin chain by Hamiltonians by definition. The only question is the reverse direction also true? In other words, are there Lux operator Frere integrable long-range spin chains or not? Obviously, I cannot answer this question, but I investigated the long-range deformation of the GLN spin chain in the first non-trivial order, and I found these Lux operators that exist for every physical parameters of alpha and beta. So I think it's a strong observation which says that this Lux operator exists for general long-range models as well. Okay, let's now continue with the finite size long-range Hamiltonians. So the main advantage of this transfer matrix, it is well defined even when the length of the spin chain is smaller than the interaction range. So it is defined even for the wrapping region. So the Hamiltonian is just the derivative of the transfer matrix, so let us calculate this quantity. So let us see an example where the interaction range is 5 and the spin chain length is 4. Taking the derivative, we obtain sum of 4 terms. And these terms are the derivative, so these blue boxes are the derivative of the Lux operator, which is just the Hamiltonian by Hamiltonian density by definition. And we can see that we can do this summation for these legs and also these legs and also these legs. So we obtain this sum. This first term is just the twisted trace of the Hamiltonian density. And the second term is a cyclic shift of the first one, and the third term is the double shift of the first one, and so on. So more generally, the Hamiltonian at order L is just a sum of a shifted version of this H1JL operator, and this operator is just the twisted trace of the original Hamiltonian density. And this is another example. So for example, if we have 8-site interaction and we want to calculate the corresponding operator at length 5, then we have to trace out these 3 extra leg. So this is the definition how obtain a finite size Hamiltonian from the asymptotic one. And by this definition, it has also a higher amount of conserved charges because these transfer matrices are commuting by definition. Okay, let us see a physical consistency condition for this definition. So let us take any finite volume long-range spin chain for every length j. It obviously defines an asymptotic Hamiltonian by taking the limit j goes to infinity. So for this Hamiltonian, we can apply the method and we obtain a finite size Hamiltonian. And the physical consistency, this new Hamiltonian should agree with the initial ones. So it's a very natural physical consistency. So let us check our method satisfy this condition or not. And we check this statement on the Inozemtsev spin chain, which is a long-range, non-long-range Hamiltonian on finite length. So this is the Hamiltonian, P is the permutation operator, and this P and zeta are the Weierstrass P and zeta function on the torus with periods j and omega. And this omega is a completely imaginary number, and this kappa is a real coupling constant. Taking the asymptotic limit, we obtain the hyperbolic Inozemtsev spin chain, which is given by this Hamiltonian. And we can apply our method to this asymptotic Hamiltonian. So this Hamiltonian contains only just the permutation operator, so we have to use this formula for this permutation operator. So this is an example for permutation between site 1 and 8. So this red box is, shows that this permutation acts non-trivially only the site 1 and 8. Using the properties of the twisted trace, and then let us set j equals to 5. So we want to calculate the 5 lengths version of this 8 lengths operator. So we can see in the wrapped case this permutation acts non-trivially on the site 1 and 3. So this is just the permutation 1, 3. And this 3 is just a reminder of 8 modulo 5. And we can generalize to the general permutation, and we obtain that this P1k is just P1 mod kj, if this residue is not 1. For 1, it's just the identity operator. So substituting this result for our formula for the finite volume Hamiltonian, we obtain that the Hamiltonian is constant plus sum of permutation times an infinite sum. And we can do this summation, so the closed form is known for this summation, which is exactly the potential of the original Inozemtsev spin chain. So we just showed that for Inozemtsev spin chain, this physical consistency condition is satisfied. So it's physically meaningful definition. Okay, let us see some requirements from the ADS-CFT duality. So my first argument comes from the fact that the anomalous dimension of the single trace operator is equal to energy level of 1 plus 1 dimensional field theory. And we know in the field theory description the asymptotic data, which is the dispersion relation and the scattering matrix, defines uniquely the finite volume spectrum. And it is not natural assumption that in the spin chain description, the statement is also true. Therefore, the asymptotic Hamiltonian is completely defined and uniquely define the finite size Hamiltonian. And we saw that the method I showed you provides unique finite size Hamiltonians. So it's in agreement with this mapping between spin chain and field theories. And my first argument comes from the fact that in perturbation theory of dilatation operator, unfixed parameter coming from the free choice of the renormalization scheme, and because it's just coming from the renormalization scheme, they cannot appear on physical quantities. Therefore, these are unphysical parameters which disappear from the spectrum. Therefore, these parameters coming from the renormalization scheme corresponds to the epsilon parameters of the asymptotic long-range Hamiltonians. But in the perturbation theory, we obtain Hamiltonian even in the wrapping region, and this parameter is still there, but the parameter is still non-physical. Therefore, this epsilon parameter should have to appear also from the finite size spectrum. And this is a non-trivial condition for a method which gives us finite size Hamiltonians. So to be more concrete, the epsilon parameters coming from the similarity transformation of an original asymptotic Hamiltonian H. And it can be proved that if we apply our method to obtain the finite volume version of this H tilde, so the rotated one, is just given by a similarity transformation of the original finite size Hamiltonian. So this Hj is the finite size version of H, and this H tilde j is just the finite size version of H tilde. So these epsilon parameters are in this uj, which is the finite size version of this original local operator. So from this argument, we can see that our method gives a finite size Hamiltonian, which the spectrum is independent from the epsilon parameters. Okay. So the second argument. So now let us consider asymptotic Hamiltonians for the n equals 4 super Young-Mills, one of the long-range deformed SU1 and SU2 spin chains, for which the SU2 subsector are the same. So choosing these Hamiltonians, let us assume the finite size version of these Hamiltonians. In the ADS-CFT, the wrapping correction of the SU2 sector includes contribution for the full spectrum. This is clear from the blue share picture, where we have to sum all the excitation, not just the SU2 excitation, and also from the quantum spectral curve, where we also have to solve the full Q system, not just the Q functions of the SU2 sector. So for the ADS-CFT, we obtain that at finite size, the restriction to the SU2 sector is not equal to the SU2 Hamiltonian at finite size, because this contains contribution for the other sectors. Let us see our definition for the wrapping region. So for the wrapping region, we have summation for these ingoing and outgoing legs. And of course, this summation belongs to the full representation of a one-side state. So the definition of these operators contains information of the full theory. So for our definition, if we calculate the wrapped, so the finite size version of a SUN spin chain and restrict to the SU2 sector, this Hamiltonian contains information from the full theory. Therefore, it cannot be equal to the finite size Hamiltonian of the SU2 model. So this is in agreement with the property of the ADS-CFT. Okay, my last argument. So the for-loop asymptotic dilatation operator in the SU2 sector contains transcendental number zeta3. But for length 4, which is already the wrapping region, the dilatation operator in the SU2 sector contains not just this zeta3, but zeta5 as well, which means that the finite volume Hamiltonian could contain extra transcendental numbers. Let us see our definition. So in this setup, so this is the 5 interaction range 5, which corresponds to the for loop, and we apply our method with spin chain length 4. So this contains a summation with this outgoing and incoming legs. And for infinite dimensional local Hilbert spaces, we have an infinite sum, which may result extra transcendental numbers. And so this is the case for the n equals 4 supernomials as well. So this definition, which contains this summation, can be in agreement with the properties of the SU2 n equals 4 supernomials. So extra transcendental can be appears. Okay, so these are my conclusions. So the main message of this talk is if we have a spin chain interaction, then we can obtain the finite size version of this interaction using this twisted trace diagram. And more specifically, I showed the perturbative construction for transfer matrices, which gives the long range Hamiltonians and higher charges. And I checked that this construction gives all the long range deformation of the SUN spin chain up to this order. And this transfer matrix can be used to define Hamiltonian with finite lengths, and we saw that this finite volume Hamiltonian satisfies some properties of the ADS-CFT wrapping corrections. The first one was that the finite volume spectrum is independent from the parameters epsilons. The second one was the wrapping correction of closed sectors depends on the full spectrum, and extra transcendental number can appear in the wrapping corrections. Thank you for your attention.
Thank you very much for this interesting talk. Do we have some questions? Florian?
Yeah, thanks for the nice talk. So if you have these GLN spin chains that you mentioned with these parameters alpha, beta, can you explicitly complete them to exactly integrable spin chains with this formalism? I mean, they are asymptotically integrable, right? Before.
Sorry, can you repeat?
These GLN spin chains that you mentioned, they are asymptotically integrable with these parameters alpha, beta. Can you complete them to exactly integrable finite size spin chains?
Yeah. So I can construct the explicit finite size version up to some order. So I calculated the Lox operator up to lambda to square. So I can construct the finite version only this lambda square. So I can obtain the higher charges as well for up to lambda square.
Okay, so you do it order by order, but in principle...
Yeah, so at this point I can calculate the Lox operators order by order at this point, but maybe in the future we have a better computation for the Lox.
And can you also get the monodromy, the deformed monodromy, or only the transfer matrix?
Yeah, so I have the transfer matrix, and these are commuting even at this finite length. So.
I mean, the transfer matrix is the trace of the monodromy, right?
Yeah.
So if you get the monodromy, you would also get, say, the deformed Yangian symmetry, how the Yangian acts on finite size spin chains.
Yeah, but in this case, the auxiliary spaces can be very high, because so the monodromy matrix so for interaction range 4, so this is the third or second non-trivial order, so we have tensor product of 3 sides of auxiliary space in the monodromy matrix, and if you go a higher and higher loop, then you obtain higher and higher dimensional subspace, and at this point I didn't analyze this higher space of auxiliary space.
Okay, thank you.
Okay, Didina also had a question. Didina, just besides.
Yeah, thank you for this nice and endearing talk. So my question was somehow related to the one of Florian. So can you give more details about the construction of the R matrix that you are using to prove that this monodromy matrix is satisfy Yang-Baxter? So yeah, the R1L.
So can you repeat the question?
How this R matrices RL are explicitly built?
So
for example, R on this formula on the screen, R1L0, what it is explicitly?
So the explicit form in R00 is just the usual nearest neighbor R matrix, and for higher order, I calculated the explicit form up to L equals 2, but these are very, very complicated, and in my paper I only put the first order, this R1, because the R2 is just, I don't know, it can be written only for 2 pages. Or
yeah, that would be nice to,
maybe it can be written in a more compact form, but I didn't try to make it a compact form.
Okay, thank you.
Okay, more questions? Okay, seems not. So let's thank Thomas once more for his.